Okay, so the two functions are f of x equals 1 over 9 times the quantity 1 plus x squared. G of x is 1/18 x squared. WebAssign says to use a graphing utility, which means use a mathematic or something like that to see what they look like. But we're going to do it without it, okay? All right, so the first one. When x is 0, we get 1/9. We have symmetry with respect to the y-axis. And another thing to keep in mind here, as x increases, this function will decrease. It's in the denominator. Not only that, no matter what x is, this thing will be positive. This function will look like this. Okay? That's what the graph would look like. And that's what Mathematica would tell you if you use Mathematica. The other function is g of x is 1/18 x squared. Well, that's a parabola, concave up. You know what that looks like. By the way, let me ask you this. What kind of function is 1/18 x squared? Thank you. Even.
Feels like a free space.
Here we go. And here's the other one. All right, to find the area bounded by the two, we're going to have to find out where these two functions intersect. Now, both have symmetry with respect to the y-axis. Therefore, the area bounded by the two will have the same symmetry. I'm going to take advantage of that symmetry and find the area from 0 to whatever that point of intersection is. Okay? And then we'll double it. Okay? That's what we're going to do. So to find the point of intersection, we'll set the two functions equal to each other. Now, this is what bothers me here about this one. I'm not sure what's going to happen here. It could be that this is where we need Mathematica just to find the point of intersection. Okay? Because I'm thinking about this, I'm going to multiply both sides by 18 times the quantity 1 plus x squared.
I think it's 1 and negative 1. If I remember from the homework, I think 1 and negative 1 is your points in the end of the...
You tell me when x is 1, it is. Oh, that is souk. That is very good. All right, this problem we'll be able to do it all right. But let's do this. I'll tell you what, let's cross multiply. Okay, how about that? Instead of multiplying by 18 times 1 plus x squared, which is the same thing, if you cross multiply, you have a proportion here. 9x squared, 1 plus x squared equals 18. Okay. Divide by 9 both sides and multiply this thing through. X to the 4th plus x squared is equal to 2. I divided by 9 and I multiplied it out. I'm going to subtract the 2. Hey! And now I can factor it. And we can factor this thing, okay? Even though it's a 4th degree polynomial, we can still factor it. I need two numbers whose product is -2, whose sum is +1. It's pretty clear cut. We're going to have a +2 and a -1 to factor it. Okay? Check it out. The fact that it's x to the 4th and x squared doesn't really mean a heck of a lot. Now, I said each factor equal to 0. X squared plus 2 equals 0. Forget about it. X squared plus 2 is not equal to 0 over the real numbers. Can't do it. Okay? Any number you square and add 2 will give you a positive number, not 0. You got complex numbers here. We don't care about those. But you set the other factor equal to 0. Factor it. And you get x is -1 or x equals 1. Just what Dylan said. Okay? This is nice. So you get -1 and 1/18 and +1 and 1/18 as well. Okay? All right, so here's what I'm going to do. To find the area bounded by these two is twice the area from 0 to 1. I'm taking this area right here, multiplying by 2, of the top function minus the bottom function. Okay? All righty.
We only go from 0 to 1?
I'm going from 0 to 1 because I'm going to take half of it and double it. Use the symmetry.
But if you use -1?
That'd be okay. But it's just easier to go from 0 to 1. It's easier to substitute in zeros than negative ones. If you got the symmetry, you may as well use it. Okay. All right, so let's do it out. Let's do the integral out. This one here is what you said. It's 1/9 inverse tangent x minus 1/18 x cubed over 3, 0 to 1. That's equal to, oh well, put in 1, so you get 1/9 inverse tangent 1. What's the arctangent of 1? What's the angle whose tangent is 1? No. Pi over 4. Okay. Minus, put in 1 here, we get 1 over 54. Okay. Then we're going to substitute in 0. Our inverse tangent of 0 is 0. And 0 cubed is 0. This is going to be our answer right here. So we get, if I can multiply by 2, multiply through by 2, this becomes pi over 2. This becomes pi over 18 minus 1 over 27. Now, how does WebAssign want this? Did they say 3 decimal places? Okay, well, I'll do pi over 18 minus 1 over 27 to 3 decimal places and put that answer in. And that's what you should have. Okay. There you go. Okay?
Did I give you a piece of paper?
Yes, you did. You get 1.7.177 question mark?
I'm going to do it because I wrote down several things and now I'm not sure exactly which one I wrote.
I don't know what pi over 18 minus 127 comes out to be, but that is the answer. That's the exact answer right there. Okay. Any other questions on homework? No?
It's a part C to it.
What?
Part C.
Part C?
Yeah, so it says use the integration capabilities of the graphing material to verify your results.
It says what?
Use the integration capabilities of the graphing utility to verify your results.
Put it in Mathematica, and you should get the same answer. You got Mathematica right there?
Yeah.
Give it a shot. Do this just like this. Put that in Mathematica, and you should get pi over 18 minus 127. Carlos?
That answer doesn't simplify anymore.
Well, not really. You can combine them into one fraction, but that's not any more simple. If WebAssign wants 3 decimal places, then you do pi over 18 and minus the 1 over 27, and you do it to 3 decimal places. It says verify your answer with computer algebra system. So,
All you have to do is put the same answer in.
what's that?
All you have to do is just put the same answer in.
And you get pi over 18 minus 1 over 27.
Well, mine was pi over 10 minus.
Oh, yeah, okay, yeah. That's it. Okay. Here we go. Are we ready to move on? Let's wait. Dylan's he's checking this out right now. No, he's not. Oh, he's doing his Facebook instead. All right, never mind. All right, let's move on. 7.2. Okay, this chapter is on applications of the integral. And what we're going to be doing throughout the chapter is solving problems. And we're going to solve problems by doing the following. We're going to have a problem to solve. For example, here's a problem to solve in 7.2. Let's suppose we have a line, and let us suppose, that this is the point H0, and this is the point HR. I'm going to use a capital letter for R. The capital letter for R means that's a constant. So we have a line through the origin that contains the point HR. That line, together with the x-axis, is going to define an area. What we're going to do is take that area and revolve it about the x-axis. What that's going to do is generate what's called a surface of revolution.
What chapter is this?
7.2. A surface of revolution. You generate surfaces of revolutions by taking areas about an axis, y-axis, x-axis, or a line. That's what we're going to be doing. Okay? And what we want to do is find the volume of that surface of revolution. Now, what will that object be? What is this object? What object do we get when we take that triangular region about the x-axis, whip it around 360 degrees? What are we going to generate? Thank you, Jim. We're going to generate a cone. So what we're going to do, we're going to derive the volume for a right circular cone. That's what we're going to do right now. We're going to derive that volume formula for a right circular cone. Because when we take this area about the x-axis, it's going to generate this right circular cone whose height is h, and whose radius is capital R. Okay? That's what we're going to generate. And we want to find its volume. So we're going to see if we can derive the formula for this right circular cone. Okay? Now, how are we going to do this? Well, we can get an approximate volume by dividing this interval up into rectangles, just like we did for area. We can divide this up into rectangles. Let's take this one rectangle. Let's say this is delta x here. Let's take this one rectangle. And what I can do is take a left endpoint or a right endpoint or a point in between, some point in here. Okay? And let's see what volume is generated by this one rectangle. We can get an approximation for the volume of our cone by summing up all the volumes generated by each of these rectangles. We'll get an approximate volume. We can get a better approximation for that volume by increasing the number of rectangles by letting the delta x go to 0. We can get the exact volume of that cone by doing what? How would we get the exact volume?
You take the area that you get from the integral and multiply by 360?
No. No, I see what you're coming from. That's an interesting thought. Okay, so I'm taking this delta x's and I'm getting these rectangles. I'm going to rotate one of these rectangles around the x-axis. It's going to generate a volume. We're going to find the volume of that, what we get. And we sum up all those to get an approximation. We can get a better approximation by taking more rectangles. We can get the best approximation, namely we can get the exact volume by doing what? Karen? That's, okay.
Formula makes a cone.
Say that again?
Getting the integral and then using some sort of circle formula to make a cone. I don't know.
Okay, getting an integral is where we're headed. But here we are here with the rectangles. We have n rectangles. You're over here getting the integral, which is going to give us the exact volume. That's where we're headed. There's a missing step. What we're going to do is let the number of rectangles go to infinity. We're going to take the limit as delta x goes to 0. Okay? When we do this, when we take that limit, as n goes to infinity, the number of rectangles goes to infinity, as the delta x goes to 0, we're going to have this infinite sum. It's going to be a Riemann sum. And I think I mentioned last time, if we can get something to look like a Riemann sum in solving a problem, okay, we can evaluate it with an integral. And that's what we're going to do. We're going to show that the solution to this problem is a Riemann sum, which can be evaluated with an integral. Okay? That's where we're headed. So you ready? Now, obviously, it's going to take a while to do that. There's a lot of stuff we got to do. So, long time. Okay, you got to do it. So let's take a look at this one rectangle. and this one piece of volume. Okay, there's one piece of volume generated by that rectangle. Well, if you take this rectangle and whip it around the x-axis, okay? When you whip this thing around the x-axis, okay, what are we going to get? We're going to get something, oh boy, I don't know how good this is. Yeah, I think you can see it. This one rectangle, whipped around the x-axis, is going to generate, oh, this is better. Okay, here's my rectangle. Okay, here's my rectangle here. Here's the x-axis here. I'm going to whip this around, just like this. Okay. What is it going to generate? What does this object generated look like? Here's my rectangle right around the x-axis. It's going to generate a what?
Circle.
A circle here.
A washer.
Oh, a disc. Okay. A disc. A washer would have a hole in it. Okay.
Oh.
Some of the things we're going to get will be washers. If we took this around this line,
And then subtracted.
that's a washer.
Okay,
Okay,
yeah,
that's
and
a washer.
subtracted the integral of the thing
Yeah.
below
All
it.
right. All right. I hear you. All right. So this rectangle around the x-axis will generate a disc. Carolina, how you doing? So, if we can find the volume of that disc right there, okay, it's really a cylinder. Okay, it's a disc of some thickness. Okay, thickness of that. We have the volume, the first volume, at least an approximation for that volume. So here we go. Call this R. The volume of this cylinder, okay, is the area of the base times the height. The height of this cylinder is delta x. This is delta x. Okay? As we whip this thing around, we get this cylinder. It looks like a tuna can. You know a can of tuna? Okay? This is exactly what it looks like. And the height of the can of tuna is this here. That's our delta x. The volume of that can of tuna is the area of the base, and it's a circle, like Dylan said. Okay? And what's the area of that circular base? What's the area of a circle? Pi r squared. So, here we go. This volume of this individual piece is going to be pi. This radius, right here, r squared, that's the area of the circular base, times the height of this, which is delta x. Okay? That's the area of that cylinder that's generated by revolving that rectangle about the x-axis. Pi r squared, area of this, times the delta x. Okay? Well, the approximate volume of the entire cone, in terms of n rectangles, would be the sum of all these volumes. Okay? Well, let's take a look at this r thing here. What is this r equal to? It's the distance from here up to here. It's the distance from here up to here. What is that distance equal to? What is that height above the x-axis equal to? Yeah, that's exactly what it is. Nice. So I can use x coordinate here, or this one, or anyone in the middle. I'm going to call this x coordinate x sub I, say. Okay, this is the ith volume. I'll call this I. So here's what we have. Our volume is approximately the sum of all these volumes of pi. And now what's this radius? It's the value of the function squared, delta x. The value of the function is this height, that's the r, and we have to square it. What do you think? Karen, what do you think? Thank you. Okay. What are you doing? Lewis, how you doing, all right? Brendan, how you doing? Okay, good. Okay. Well, We can get better and better approximations by taking more and more rectangles, by letting delta x go to 0. We can get the exact volume by taking the limit as n goes to infinity of this sum, of all these. This is a Riemann sum. Okay? It has the form we need. The form we need is a limit as n goes to infinity of a sum of some function of x times a delta x. The fact that we have pi in here doesn't really matter. Take the pi out front, it's a constant. This is a Riemann sum. How do you evaluate that Riemann sum? You evaluate it by realizing that this Riemann sum is the area under some curve, namely the curve whose function is pi f of x squared. That will generate a function. Hey, Sam. Okay. This will be the area under that curve, whose function is pi f of x of I squared. And how do we evaluate that? With an integral. That's what we need. Or you can state it this way as well. It may be easier to remember this way. R is equal to f of x. Okay? This is what we're going to use to find volumes of solids of revolution when, by taking a rectangle and whip it around the x-axis, we generate a disk. Because that's what happened here. We ended up with that disk of thickness delta x. Whenever that occurs, we can use this formula to find the volume of that solid of revolution. Let's do it for this case. You ready?
So delta x is d of x?
Yes, that's what it amounts to.
That's the change in.
Yeah, that's exactly what it does. Okay, you ready? Oh, I can see overwhelming support for this.
Let's do that pizza.
What's that?
Maybe it's a pizza like that.
I know. I ordered this week. I ordered 2 cheese and 1 combination.
Mr. Brooks, can I see that?
Oh yeah, there you go.
It'll still be about 15 minutes late, 20 minutes late.
Yeah. Oh well. Okay, so you ready? Let's do the problem. The problem was to take this function straight line okay, and I said that x was equal to h, and this is capital R. Okay, so this point right here is HR. I want to take this, whip it around the x-axis, generate that right circular cone, and derive the volume of that right circular cone. That volume is going to equal pi times the integral from 0 to h. Our function. Now, what is our function? We don't even know what our function is. We know it's a straight line that passes through the point HR and the origin. What's the equation of this line? What is our function here?
It's going to be in the form y equals m.
Yeah, y equals mx plus b. So what's our y equals?
R over H.
You bet it is. Thank you. R over hx. Slope is r over h. Okay, it goes through the origin, change in y over the change in x. Since it goes through the origin, b is equal to 0. Is everybody okay? Okay, that's our function. Y equals r over hx. Okay, what are we going to do? We're going to square it. That's what we said we had to do, delta x. Okay. Why? Because when we take this rectangle right here and whip it around the x-axis, we're going to get a disk. And if that's the case, this is the formula we're going to use. Okay? So, pi, 0 to h, r squared over h squared x squared dx. Bring these r's and h's out front, they're constants. I'll tell you what, before we do the integral, what answer should we get? What is the volume of a right circular cone whose height is h, whose radius is r?
4/3.
Yeah, let's just,
Yeah, you go here. We want a right circular cone.
pi, height times pi times radius, but I guess is there a 1/2 in there?
There's something there. We'll see. Brennan?
1/3 pi radius squared height.
Yes. Okay. Here's the deal. You actually should know this. We're going to derive this right now. Thank you, Brennan. But what you should know is this. I think I don't know. I can't believe I haven't mentioned this before. But here we go. If you have an object, three-dimensional solids, okay, and if they come to a point, cones come to a point, pyramids come to a point. Okay. The difference is cones have circular bases, pyramids have polygons for bases. Okay. The volumes of those solids is 1/3 the area of the base times the height. You should know that somewhere along the line. Okay, you should know that. You should also know that if it doesn't come to a point, and now we're talking cylinders and prisms, and again the difference is in a cylinder you got a circular base. In prisms you have polygons for a base. Okay. Polygon here, it doesn't have to be a square even, it could be triangular, it could be a pentagon or something like that. And it could be a congruent pentagon, it doesn't even have to be directly above it, it could be over here, pentagon, congruent pentagon over here. The volumes of those solids, okay, cylinders, okay, and prisms are area of the base times the height. Come to a point, 1/3 area of the base times the height. Okay. Spheres, a category all by itself. The volume of a sphere is 4/3 pi r cubed. Okay? Those things you should know, especially your Calc 2, for Pete's sake. Never mind all three you should know. I can't even get into that, but just saying. Just saying. All right, so what we should end up with is deriving the volume of a cone, which is 1/3 the area of the base times the height. The base is a circle, pi r squared. We should end up with 1/3 pi r squared h. That's what we're deriving. That's what we should end up with. Okay? Let's try it. Let's do it. So I got pi r squared, h squared. The integral of x squared, x cubed over 3. We're going from 0 to h. We got pi r squared, h squared. Okay. Substitute in h, we get h cubed over 3. Substitute in 0 to get 0. Well, h squared, h cubed. Okay. What do we end up with? 1/3 pi r squared h. That is the volume of a right circular cone. We have just derived that formula. Okay? We've just derived that formula. The bottom line is, anytime you have a surface of revolution where those, with a rectangle whipped around the axis, okay, is going to give you a disk, you're going to use this formula for volume. The volume is equal to pi r squared dx. Okay? That's in your integrating with respect to x. Okay? We'll do one where we integrate with respect to y in a second. Let's do another problem with this, though. Okay? You ready? Okay. Let's do another one. Let's do one where there's no formula for it. This one we knew there is a formula, so you didn't need to get the calculus to do it, because there's a formula for cones, okay? Let's do one where there is no formula for the thing, okay? So here we go. Let's say you're, we can make up a problem too. Say you're an engineer working for Smith & Wesson, and they're designing a new bullet, okay? And the bullet has this shape. Okay. This is the shape of that bullet. It's this area whipped around the x-axis. Okay. That's what the bullet shape is. Okay. Okay. I don't know how realistic that is or not, but let's assume that's what you're doing. And you're one of the engineers working on this design, and we need the volume of the thing. One of the fundamental properties of this bullet is how much space does it take up? What's the volume of this thing? Okay, well, let's see. Here's what you do. You take a rectangle, put it in here. When this rectangle is whipped around the x-axis, what does it generate? A disk. A disk. Okay. So we can use this little formula. This is the volume of solids of revolution where we get disks. That volume is equal to pi, the integral, from 0 to 4, r. R is this distance here. It's the function itself, square root of x squared dx. Okay? That's equal to pi, 0 to 4, x dx. That's equal to pi, x squared over 2, from 0 to 4. 4 squared is 16. The 0 was 0, so you get 16. You get 8 pi. The volume of this bullet, this thing generated by taking the square root of x, revolving around the x-axis, that volume is exactly 8 pi cubic units. That's its exact volume. Okay? How are we doing? We doing okay? Now, here, let's do another one. Let's suppose we take this. Let's take y equals x squared. Here's y equals x squared. Let's take this piece of it. Let's go from 0 to 2, say. Let's take this area around the x-axis. Okay. I want you guys to do it. Find the volume of the solid of revolution generated by taking this area about the x-axis. You guys do it. It's y equals x squared, 0 to 2. Go ahead.
So the distance from 0 to 0?
0 to 2. Yep.
The point on top of that, is that 0, 2, 4? The point
2, 4. Yep. I will even draw it for you. Oh, I know where you're working now. You're working at Hershey's. And you're designing a new Hershey Kiss, okay? And you need the volume. Because what we're going to do is see if we can decrease the amount of chocolate that we need to make these guys, okay? Save some dollars.
Let's make them fat. Let's make them bigger.
No, that'll use up too much chocolate. We're going to make them real thin and, no, I don't
No,
know.
we need husky Americans.
Jeez, we have husky Americans. We have.
No, so we need to put air bubbles inside of them.
Oh, there's an idea.
There, do it.
Yeah. What? Oh, they already do it? Yeah. So we need a thin veneer of chocolate on the outside and mainly air inside. That'll save us some money. Yeah, that'll do it. You have it? Yeah, our Hershey Kiss thing. No. That looks perfect. Except for one thing. On the 5 you can see. It's not.
Students make the most of those.
Yeah, that's okay, let's take a look. Got it?
I tried.
Okay, so what'd you get?
16 pi.
No.
32 pi over 5.
32 pi over 5. Perfect. Okay,
Yeah,
no.
I should have gotten it.
I agree, you should have gotten it, Dylan. Okay, here's the thing to do. Put a little rectangle in there, whip it around the x-axis, recognize that you're going to get a disk. The volume, therefore, is pi, the integral, 0 to 2, r squared, okay, the function squared, dx. That's pi, x to the 5th over 5, 0 to 2. 2 to the 5th is 32. 32 pi over 5. That's the exact volume of that solid of revolution. Okay? Yes?
Can you explain the putting in the rectangle? Is that just to see if like you get your height h with it going?
Yeah, the rectangle is to make sure that we're getting a disk when we evolve that rectangle around the x-axis. Because the very next problem I'm going to do, we're not going to get a disk. We're going to get something else. Consequently, we're going to have to use a different formula.
Elaborate on getting a disk, though.
Well, when I, see, we're in here in the very beginning. Wait, where's my first piece of paper? Do you have my first piece of paper?
Yeah.
That first piece of paper, here, and I don't know how good that is. When you whip this around, here's what I did. Maybe, hopefully this works. This is my rectangle, okay? This is the x-axis here. When you take this rectangle and you whip it around the x-axis like this, what you're getting really is a cylinder. It's got a circular base here, and a height that's here. It's called a disk, okay? It's a disk. It's a disk with some thickness. It's a cylinder, but it's called a disk method, okay? It's called a disk. The volume of that disk is equal to pi r squared times delta x. That's how we generated the formula for this.
Okay.
Pi r squared delta x, where r is the function itself. This height above the x-axis is the value of the function at this point.
Okay.
That's what we did.
Thank you.
Okay. I lost. Jimmy's not here. Oh, here he is. Okay, good. They wanted me to go ahead without you, Jim. I had to tell them no. I got to wait for Jim.
Thank you.
All right. All right. Let's try. All right. How's this? Is this reasonable or what? This looks pretty straightforward, right? Lewis.
So for a non-disc, what would it be?
Well, let's see what happens. Let's take another problem here. Let's do this. I'll tell you what. Let's take y equals x squared, the same thing. But instead of going around the x-axis, let's go around a line y equals -2. See what happens here. So we're going to take the same area, y equals x squared. Okay, to here. Hey, how you doing? Good. We're going to take the same area here, but now we're going to whip it around this line y equals -2. So this area is going to get whipped around that line. Will the volume so generated be equal to, greater than, or less than the volume that's generated by taking the area around the x-axis?
Now, is there going to be equal spacing between the x-axis and y equals -2 on the top and the bottom?
Yes. So when you whip this around, you're going to get, on the other side of this,
So then what we just subtract
we're going to get this.
pi 2 squared? Isn't that going to be the area that we take out, right? That circle in the middle?
Well, it's a cylinder in the middle. Yeah, we could think of it that way. Okay, I know what you mean. I got it. Okay, but the point is, first of all, the volumes are going to be different. It's going to be greater now. Okay? When you take a given area about a greater distance, it will generate a greater volume. Okay? That's fundamental. Let's take our rectangle and let's see what happens to our rectangle. Yes?
Just like if it was below the x-axis, it would be less than?
If you take this area, all right, so tell me what you want to do.
Well, I'm saying the opposite of what you said.
Okay, then I agree. Okay. Okay. So, here we go. Let's take a little piece here, this rectangle, and whip it around the line y equals -2. We don't generate a disk anymore. What we will generate, okay, here's the line y equals -2. What we will generate is something like this. Let's say if I can draw this here. If I can draw this, I will be good. Okay? I will get something like this. Okay? This is my x-axis up here. This is my rectangle. When I take that rectangle now, here's my rectangle. Okay, here's my rectangle. Here's my x-axis. Okay. Here's the line y equals -2. I'm going to take this about the line y equals -2. It's going to generate this. Okay? That's what it's going to generate. That's what that thing is supposed to be. That thing is called a washer. Okay? It's a washer. What is this washer? Well, it's the difference of two disks. It's got an outside disk. Okay? From here to here, the outside disk minus the inside disk. I'm going to call the outside disk the disk having radius capital R, and the inside disk has radius little r. Okay? The volume that's generated by that area is going to be the volume generated by the outside disk minus the area generated by the inside disk. That's what we're going to get. So here's what we got. That volume, okay, is equal to the limit as n goes to infinity of the sum of all these individual pieces of volume. There will be outside volume, which will be pi capital R squared minus pi little r squared, each of which times delta x. Are you still on there? Yes. Okay. All right, so I got big area, pi r squared delta x, capital R, small area, pi little r squared delta x. Take the difference, that's going to be the volume in question. That's the volume of that one piece generated by that one rectangle. And then I'm going to sum up all the pieces that I get from all the rectangles. Okay? And then I'm going to let the number of such things go to infinity. The question is, do I have a Riemann sum? Do I have some function of x here times a delta x? And the answer is yes, I do have a Riemann sum. And how you do this Riemann sum? With an integral. Here's the volume for washers. This is washers now. Okay, this is for washers. The volume is equal to pi, the integral from a to b, big R squared minus little r squared dx. And again, we're going around the x-axis or something perpendicular to the x-axis. Okay. These rectangles are perpendicular to the x-axis. All right? At some point, we're going to go around the y-axis, too. All right. Everybody see this okay? Let's do it. Let's take this problem, take the same area we just had. When we whipped it around the x-axis, we got a volume of 32 pi over 5. Now we're going to take the same area around the line y equals -2. We will get a bigger volume because that same area is going around a greater distance. So let's see what happens here. Okay. Yes. Wait, everybody okay with this?
One more second.
Okay, no problem. Is it warm in here or what?
A little bit.
A little bit?
Yes. I had my windows open in the house today because I went out on my porch, it was like 65 degrees.
Boy, it's warm. It's warm in here, I tell you. Phew. Louis, you're all bundled up. I can't believe it. How do you listen? Okay. All right, how are we doing? Let's do it. Are we doing okay? So the volume is equal to pi times the integral, 0 to 2. Big R, what the heck? Here's our diagram here. What the heck is big R? In this case, big R, this is big R here, okay? That's the big radius. Little r is this distance, okay? We got big R from the axis about which we're revolving to the top of the function. Little r is from the axis to the bottom of the function. Can someone tell me what big R is equal to?
Little r plus delta x.
No. No. Delta x is going this way.
Oh, okay.
Oh, delta y?
Well, can someone give it, what is that? That.
2.
Okay, here, let's take a look. Let's go back here, okay? Big R is from here up to here. Now, in the previous example, we went from here to here, and we said that was our function, which was x
Oh, yeah,
squared.
so it's definitely
It's x squared plus 2.
So it's x squared plus 2, yeah. Who said that? And you're pointing up, so he's, oh, I see. All right. All right, okay, so here we go. Okay, what we have for big R is this distance here, which we said was the value of the function. It's the height above the x-axis, plus this distance 2. So it's x squared plus 2. X squared plus 2. So that's big R. So here's the general form. Big R is our function plus 2, and we're going to square that. What the heck is little r here? 2. It's a constant. This integral will give us the exact volume of that solid of revolution generated. Okay? That thing with the hole in the middle. Okay? That's equal to pi, 0 to 2. Multiply it out. X to the 4th plus 4x squared plus 4 minus 4 equals pi, 0 to 2. X to the 4th plus 4x squared dx. That's equal to pi, x to the 5th over 5 plus 4x cubed over 3. Ugh. From 0 to 2. Yikes. We get pi. We get 32 fifths. Oh, that's what we had before. But we get an additional amount. Plus 2 cubed is 8 times 4, 32 thirds. Okay. We get, we go to 15ths. We've got 96 plus 160, 256 pi over 15. Okay. That's it. That's the exact volume of that solid of revolution. Okay? How's that look?
Neat.
It is. What's that? It looks, is it, okay? I'm going to give you guys one to do. You ready? Okay, here we go. Let's take, let's just keep it simple here. Let's take y was x cubed. Let's go from 0 to 2. Let's take this, and I want to generate a solid of revolution by revolving that around the line. Let's just go y equals -1. Okay. Find the volume of that solid of revolution. Yes,
0 to 2, right?
0 to 2. Do 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 do.
The x is 2 comma 0.
Yeah, on the x-axis, it's 2 comma 0. JD, you have it?
No. I don't.
What?
I think I did it wrong.
Oh, no. Lewis?
That negative 2 squared, the top there, where'd that come from?
It's minus 2 squared?
Yep.
That comes from the fact that we had a space of 2 units here. That's our little r, is 2.
Was that a con?
Is that what?
Like, is that in the original formula you gave us?
The formula is big R squared minus little r squared. The
So
2
that
is the little r.
Oh, okay.
What's little r in this case?
Negative 1.
It's 1. 1. You got it. 1, yeah.
Squared, yeah.
Yes. Well, the fact is 1. The distance between negative 1 and the x-axis is 1 unit.
Unit.
Yeah, 1. You're squaring 1.
Okay.
You sure about that, huh, Brendan?
I think so.
I'd put money on it.
Thanks.
I got some. I have 50 cents. What the heck? I had 50 cents. I don't even know. What was that? That was a weird coin. Oh, it's American too.
Saying that all the way coins come from other countries?
Well, I'm saying I'm not familiar with this coin. It has a. It says it's a. It certainly looks like a great blue heron on the back, but it's got a great blue heron on the back. I don't know if you can see it. It says it's a Bombay hook. It looks like a great blue heron to me, but this is a 2015 quarter. I didn't realize our coins now had birds in the back.
We do state birds.
Is that what it is?
I'm guessing.
I mean, they ran out of states, so they had to do something, right?
Okay. Oh, see, this quarter has. Says Delaware. Okay, so this one says Delaware. So there's a state, but this one has a bird here. No, I had no idea.
Put it on the overhead, we can all just look at it.
What's the name of the bird?
It looks like a great blue heron, but it says Bombay hook. Maybe that's this place where this thing is found, but it definitely is a great blue heron now.
Okay. So,
I don't know if you can see it, but that's a great blue heron. Okay. And it says Bombay hook here. I bet you Bombay hook is a place. Does anybody know this place?
Yeah, they do landmarks now.
Is that what it is? Landmark.
It's actually in Delaware.
Yeah, that's funny. Okay, that's pretty cool. All
You
right.
know, it's a conservation center.
Oh, well, that's pretty cool. They do
It's,
landmarks because that's definitely a great blue heron.
It's one of the largest remaining
expensive tidal salt marsh in the mid-Atlantic region.
Cool. Wow. Well, that's where you would find a great blue heron, that's for sure. That's pretty cool. I didn't even realize we were doing that. Wow. Huh. Things you learn. Okay, how are we doing?
Good.
We got some answers people are pretty proud of? Yes.
I got 72 over 75.
72 sevenths pi. Is that what you got? Anybody want to disagree with that? Sam?
56 pi over 3.
56 pi over 3. Egg?
72 pi over 5.
72 pi over 5.
184 pi over 7.
180.
I got
Oh! Oh, wow.
What?
100, what'd you get, Brendan?
184 pi over 7.
184 pi over 7.
Oh, no.
You got a lot of support there, too.
Yeah.
Let's check it. Let's do it. Let's take this little rectangle in this area. Now, what's this rectangle going to generate as you whip it around the line y equals -1? What does that rectangle generate? A washer. That's the first thing to do when you're doing these problems, okay? It's the first thing to do. Put a rectangle in the area question, revolve it about the line, and see what it generates. It's either, right now, it's either going to generate a disc or a washer, okay? We have one more thing that's possible for the generator. There's only 3 shapes that are possible, 3 objects that are possible. We haven't done the third one yet. We'll do that momentarily. Okay? So we're going to get a washer, and realizing it's a washer, you know the volume is pi, integral from a to b, big R squared minus little r squared. Okay? So let's do it. Pi, the integral from 0 to 2, big R. Now big R is the from here, the top of this, to here. What is big R equal to?
X cubed plus 1.
X cubed plus 1 is correcto. We're going to square that. Minus, what's little r equal to?
1 squared. Or what, -1?
1 squared. Okay? That integral will give us the exact volume of that solid of revolution. Multiply it out. X to the 6th plus 2x cubed plus 1 minus 1. Okay? Those cancel. Integrate it. X to the 7th over 7 plus 2x to the 4th over 4. It's over 2 then, okay? Knock out some 2's. 0 to 2. Okay? So we get pi. We get 2 to the 7th. That's 128, I think, over 7, plus 2 to the 4th is 16 over 2. 16 over 2, which is 8. And the zeros give us 0. We got to go with 7. Here, we're going to combine these into 1. So we're going to go with 7. We got 128 plus 56. That's 184 pi over 7.
I subtracted some adding.
Shoot. So if you're an engineer and you were finding the volume of an airplane wing and you had a little minor mistake there, the airplane would fly tilted like this and go right into the ground. All right, but anyhow, are we all set on this? Okay.
Wait, then, on the...
What's that? What? What is it?
No, I thought we were done.
You thought we were done?
Yeah.
Oh, we got hours to go. We got a whole bunch to do today. Oh, man. Long ways.
Wait, so you got the washer, you got the other thing.
We got one more thing. We got another thing, yeah. I'm going to do the other thing. What's that?
Is it like a strip?
A what?
What else do you have?
It's called a cylindrical shell. We're going to do that next.
Oh,
You ready?
Sure.
Okay, let's do it. Okay, we all set here? Okay, here we go. Okay, so far everything we've done has been around the x-axis or something parallel to the x-axis. Let's do something different. Tell you what I want to do. I want to go back to our first problem. Okay. And this, we said, was y equals and we did the slope, okay, r over h x. And when we whipped it around the x-axis, we generated a right circular cone, and we derived the volume. We found the volume to be 1/3 pi r squared h. That's what we found it to be. That's the volume of a right circular cone whose height is h and whose radius is r. Okay? Now, here's what I want to do. I want to take the same area about the y-axis. Okay? I'm going to take this about the y-axis. When I take my rectangle and whip it around the y-axis, this is what I'm going to get. I'm going to get this. Okay. This is what I have. This, here, wait a second, I can do this better. Yeah. Okay, this is what I've got. Shoot, I should have extended it. It's out. This is not the best drawing. What's that?
Are you going to start making like YouTube art videos next?
No, I should. No, I should. Not with this one. I didn't do this one really well. Okay, but what this is, here's what we got. Here's what we have this time. This is our rectangle. Okay. Here's our x-axis. I'm going to take this around the y-axis. This thing around the y-axis. It's going to go around like this. Okay? That's what it is. No, you don't like that? That's what it is. Trust me. Okay? It's going around like this. That is called a cylindrical shell. Okay? Yes, Carlos.
Isn't that 3D?
3D? Yes. But so is this, and so is this around the washers and discs are all three-dimensional objects. This is a three-dimensional object as well. They're all three-dimensional objects. Jacob.
Well, but how do you get that shape?
I'm taking my
A
rectangle.
triangle.
What? Well, I'm just taking this one rectangle. Taking this
Stop.
rectangle right here. Here's my rectangle right
Yes.
here. Okay? And I'm taking it around the y-axis. That one rectangle will generate this.
But isn't there
Yeah, the
another
next one, the
rectangle?
next rectangle will generate one that's a little bit bigger, and then a little. Yeah, but forget about those.
I mean, are we talking about a... Is there no slope to the rectangle? Does it not have a width?
The rectangle here, yeah, it is sloped, but we don't care. We're going to approximate it. It's only an approximation. We're just going to take like the left endpoint or right endpoint or someplace in the middle. You're absolutely right. That's why these are approximations. I don't have exact things here.
Before we start, would it make more sense if you just revolved it like it was a square and then figured out the area that would be in the middle of that and then just sort of take that way?
No. That's the short answer, Dylan. No, it is slanted. He's right. I mean, it's not a perfect rectangle. We know that. We knew that from taking rectangles, finding the area under a curve. It's slanted. But you're going to take a left end point or a right end point. Does it matter? No, it doesn't matter, because when we take the limit as n goes to infinity, that delta x goes to 0. It will not matter.
It'll be a line.
Yes, it'll be yes.
Okay.
It won't matter. You're going to have to trust me on that.
No, that's fine. I didn't.
No, that's okay. No, that's okay. The thing wrong with my diagram here is this is the thickness delta x, not just this little part here. So I don't like my diagram. It really is this That's my rectangle, and this is my rectangle here. Okay? The rectangle goes out to here. I like that better. It's this, whipped around this, like this. Okay? So what do we have to do? We have to find the volume generated by that rectangle as it goes around the y-axis this time. We have to find the volume of that cylindrical shell. Now, it's like tuna can, okay? It's a tuna can here. How are we going to find the volume of that tuna can? It's a tuna can with thickness delta x, okay? The thickness of the tuna can is delta x. How are we going to find the volume? Here's what we're going to do. Consider this. Cut the tuna can up the side. Okay? Cut it. Open it up. Tuna can. Okay? This way. What are we going to have? We're going to have a rectangle with thickness delta x. What's the volume of that rectangular solid of thickness delta x? It's the area, length, times the width, times the height of delta x. You with me? What's the length?
The circumference.
No.
The circumference.
It's the circumference, which is
2 pi r.
2 pi r. No, Healy already said it. You were saying it, right? Yes. No, Healy was saying it. Okay. It's 2 pi r. It's the circumference. Okay. Okay. It's the circumference of this. When you cut it and open it up, that length is equal to the circumference 2 pi r. So here's what we have for a volume. The volume of that cylindrical shell, that one piece right here, this one piece, is 2 pi r h. This will be h. This is r delta x. Okay? Because when you cut that up, cut that and open it up, you got this rectangle. Length times width times the depth will be the volume of that shell. Okay, so what's the approximate volume of the rectangular of the solid generated by rotating this around the y-axis? That volume, in terms of n of these, is going to be the sum the exact volume is equal to the limit as n goes to infinity of this sum Now, here's the deal. Got to make sure that what we have is a Riemann sum. To have a Riemann sum, we have to have an infinite sum, and we do. We have to have a function of x here and a delta x. Well, we have our delta x. The 2 pi is a constant. We could take that all the way out front. The question is r and h, are those functions of x? Well, what is our h here? Our h is equal to the function itself, whatever the function happens to be. Okay? In this case, it's the value of the function here. And what's this r? What's this distance from? What's the distance from the y-axis equal to?
Why?
No. What is it? X. That's what an x-coordinate is. It's a distance from the y-axis. Okay? So here's what we have. I think what your best bet is for shells. This is called cylindrical shells. The volume is equal to 2 pi integral from a to b r h dx. I think that's the best way to remember this. Okay, 2 pi r h. Okay. That 2 pi r h is that area of the rectangular strip. The delta x is the thickness, giving us the volume. So here's what we're going to do. Watch this. I'm going to take this area, whip it around the y-axis. Now, when I whipped it around the x-axis, I got 1/3 pi r squared h. When I take this around the y-axis, will I get 1/3 pi r squared h again?
Well, you don't have any squared terms, so the integral is not going to have a...
Well, I didn't have any square terms when I did it the first time. I had the line y equals r over hx. I whipped it around the x-axis. We generated a volume of that. We generated that right circular cone, and we found its volume to be 1/3 pi r squared h. That's what we derived from that function. My question to you is, if I take this very same area around the y-axis now, will it generate the same volume? Karen?
Will it make the same volume?
Yes, will it have the same volume as pi, well, it'll be 1/3 pi r squared h.
I didn't know that was what you were asking.
Oh, where did you think I was at?
I thought you were asking if you would use the same formula.
Well, no, because I'm going to use cylindrical shells now, so I'm not even going to use the same formula. But it's possible I use a different formula but come out with the same answer.
What's the angle?
I don't know. But I don't care. Okay. The angle is the inverse tangent of r over h, but we don't care. Doesn't matter. So here's the thing. I'm going to generate a cone again, right? When I take this area around the y-axis, it's still going to generate. No, it's not going to generate a cone. What does it generate? It generates.
Like a
Well,
base.
the individual rectangle generates a shell, but the triangular region generates.
Inverse? Like a
Yeah, something
base
else. What is it?
A base.
A vase.
Yeah. The
Okay.
A circular vase, this coming in like this. Okay?
It's an inverse.
Yes.
pyramid.
Yes, like that.
Yes, I agree.
Oh,
So the volume is probably not going to be the same. Okay?
could you find the same
We're going to do it. What's that?
Could you find the same function by taking the inverse of the x function?
Say it again. What do you want to do now?
But take the inverse of the
That function?
No, of the x-axis function.
What do you mean by that?
I think he's saying take the inverse of like the y equals r over h.
Well, that's what I just said. You said no.
Oh, but then like integrate that over the x-axis.
I think you're
Go
getting
take
too
the
complicated,
integration form and
Jacob.
take the inverse.
Here's
of the
what we're going to
integration.
do. We're going to take I'm going to use the cylindrical shells right now. We'll just do it. Yes?
It would be like 2/3 that instead because like the cone would fit inside.
Yeah, that's the kind of thing we're going to get. What we have is a cylinder with a cone removed. And you know the cone has 1/3. And you're saying take the cone out and we should get 2/3. Because the volume is, let's check it out. Let's do it. Okay, you ready? Okay. Volume is equal to 2 pi, the integral. Where are we going? From 0 to h. Here to here still. R. Now, you got to be careful. Here's R. Okay. R is this right here. It's this right here. That's R. Okay. When I take my rectangle, sitting on the x, here's the y-axis. I'm going around the y-axis. Okay. What is R? It's this distance to the y-axis. From here to the y-axis. What's that distance from here? Yes, it's x. R is x. This distance is x. The distance from the y-axis is x. H is this distance here. That's the h. Well, it's f of x, which is equal to r over h x. There's my f of x. There's my function. Oh my gosh. Okay, I'm working like a dog here. Okay. All right, you ready? Is this, all right, you're going to have to check this out. Does this make sense? Is this the kind of thing you're going to have to do these problems? You're going to have to take the area in question. You're going to have to draw a rectangle. You're going to have to whip the rectangle around an axis, x-axis or y-axis, or about a line, and you're going to have to figure out what that rectangle generates. There are only three possibilities. It'll generate a disc, a washer, or a shell. And let me tell you something. If the rectangle that you have is parallel to the axis about which you're revolving, it's going to be a shell. This is parallel to the y-axis. It's a shell. If it's perpendicular to the axis, it'll either be a disc if there's no space, or a washer if there is a space. Okay? That's it. You can't get anything else. Okay? And all these solids of revolution, you're going to get one of those three. All right, so let's see what we got. Let's see what we have. So the volume is 2 pi.
This is because you just take a shape and it's just revolved around an axis and you're guaranteed to get.
You're guaranteed. Yes?
You said perpendicular and no space is
It's either a disc or a washer, depending on whether you have any space in between.
So if there's no space.
No space, disc. Space, washer. Okay? Disc, washer. Okay? Disc, washer. Okay. All right, 2 pi r over h, 0 to h, x squared dx. Bless you. Somebody's allergic to shells, I see. All right, that's okay. It's all right, it's possible. 2 pi r over h, x cubed over 3 from 0 to h. Substitute it in. So we get 2 pi r over h, h cubed over 3. Let's see what happens. This cancels with this. We get 2/3 pi r h squared. Now, you gotta be, this is exactly what Mohit was talking about, though. But why is it r h squared? Because the cylinder now, the cone, what's the radius of the cone? The radius of this cone as you whip this around is the h part now, not the r part here. Okay? Because when we whip this around the y-axis, the radius of that is this distance. As you whip this around, that's the h. That's why the h is squared and not the r. But it's 2/3, just like he said. If you take the cylinder and take the cone out, what's left is 2/3 of that volume. Okay, here we go. We're taking out this, at the risk of making this even more complicated, okay, we're taking out this part right in here. And what's left is that 2/3 part. Okay?
Does that mean a cylinder is pi r h squared?
The volume of a cylinder, pi r squared h. Okay? That would be this, pi r squared h minus the cone right in here in the middle. Our triangle's on the outside, and it's equal to the volume of the cylinder minus the inside cone. And that's 2/3, that's what he said. Okay, so how you guys doing? Okay, here we go. Let's take a look at this. Crank it up a little bit. Let's take a look at the volume generated by taking let's take y equals x and y equals x squared. Let's take this area about the x-axis. Okay? Let's take this area about the x-axis.
Would you write inside the parentheses?
What's that?
Inside the parentheses.
1, 1.
1, 1.
That's where they intersect. Okay. Here's the rectangle inside this area. Okay. We're going to take this rectangle about the x-axis. What does that rectangle generate? Well, we're you know what? We're not even going to use the Riemann sum anymore because we've used the Riemann sum to generate our 3 formulas. We have 3 formulas to use depending on what we get. We have our disk formula, pi, the integral from a to b, r squared dx. We have our washer formula, pi, the integral from a to b, big R squared minus little r squared dx. And we have our cylindrical shell, which is 2 pi, the integral from a to b, r h dx. That's what we have. We have one of those 3. We use the Riemann sum to derive those. Now we don't need the Riemann sum anymore. Now what you should be doing is looking at this and saying, okay, that rectangle, as it goes around the x-axis, will generate what? A washer. Okay? Is that what you said? That's what you said. So, okay? It's going to generate a washer. That disk, that rectangle around the x-axis is going to generate a washer. It's perpendicular to it. It's either going to be a disk or a washer, and there's a space. Okay, so it's a definite, it's a washer. Okay? All right? Is everybody okay? You guys can do it, right?
Yeah, you just.
Yeah, go ahead. Go ahead. You guys do it. Find the volume.
I gotta leave. Sorry.
It's your call, man.
I'm not supposed to come. I had to stay in hospital for like all night.
Oh, I'm sorry.
No, not for me. One of my friends is sick, so
Still, I'm sorry. I'm sorry you had to do that.
still try to come. I can't.
Yeah.
I can't focus.
I gotta go sleep.
Okay.
Probably gonna see the video. It's on YouTube.
The video is not going to get up until Monday. Okay, because I won't see him until Monday.
Khan Academy, I guess.
Khan Academy has stuff. Yeah, Solids of Revolution. Definitely look it up.
Thank you.
Khan's not as good as I am, but
Yeah. Alternatives.
Is it revolving on what axis?
X. We're going to do the Y next. X right now. Got it? Oh, the only problem is, you end up with a negative. That's definitely, you're not, there's no way. And the reason is, because the top one is the x, and the bottom one is the x squared. So it's the other way around. So you just got to do the opposite of what you got here. Yeah, it looks so good. Let's see what Karen, she's busy. Oh, it's not sure. But I'm curious, because she said 5 minus 3, and then she put 8, so I don't know what the heck happened. Well, then she comes up with the index.
Man, I'm so tired. I haven't seen this.
Yeah, looks pretty good. That looks pretty good. Yeah, you did, somewhere along the line. Okay. Okay, you guys ready? Who's got an answer he or she is pretty proud of? Karen?
215 pi.
2/15 pi. Anybody want to disagree with her?
Yeah, pi over 30.
Oh, you got pi over 2 times the 15. You got pi over 30. Now, Brendan's pretty formidable adversary. So,
I didn't feel too great about this one.
oh, you don't? Anybody else want to put his or her 2 cents in?
7 pi 15.
What is it?
7 pi over 15.
7 pi over 15. All right. Anybody else? Yes.
2 pi over 15.
Ooh, look at that. Okay. Let's take a look. Let's do it. We're going to whip this around the x-axis. First thing to do is realize what we have is a washer, the volume of which is pi a to b, big R squared minus little r squared dx. Okay? And I must point out, we get a dx here because this little width of this little rectangle is a delta x. What we're going to do soon, in the next 2 or 3 hours or so, is to flip this rectangle around and have delta y. But we are going to do that, but it'll be sooner than that. Okay? It'll be a delta y there, and everything will have to be in terms of y. But right now, everything is in terms of x. When we take this rectangle around the x-axis, it will generate this washer. This is the formula we're going to use. Let's do it. Volume is pi, the integral from 0 to 1. Big R. Now, big R is going to be this distance right here to the top function. This is big R. And big R is equal to x. Little r is the height to the bottom function. And that is x squared. And we're going to square that. This is what you should have. This integral gives us the exact volume of that solid of revolution. Okay? So, we get pi, x cubed over 3, x to the 5th over 5, 0 to 1. We'll get pi. We're going to have 1/3 minus 1/5, which is equal to 2 pi over 15. Okay? And that's it. Now, let's take the same area and let's go around the y-axis. Okay? When we do that, what shape do we get generated by this one rectangle? This rectangle will generate what?
Cavity.
What?
Cavity.
A cavity. And it'll hurt. So we shouldn't do it that way. All right? No. It's not a cavity. You call it something else. A shell. Don't call it a cavity. What the heck? All right. It's a shell. It's a cylindrical shell. That's what you meant. I know that's what you meant. Okay? Because it's this rectangle around the y-axis. It's a shell. When the rectangle is parallel to the axis, it's a shell. Always. When it's perpendicular, it's either a disk or a washer. Okay? So let's do it. This will be our R now. Our H is this height of that rectangle. So the volume. Now, it's difficult to say if the volume is going to be greater than, equal to, or less than. Okay? It's not necessarily equal to, but it's probably going to be greater. And the reason it's probably going to be a greater volume is because this area is closer to the x-axis than it is to the y-axis. So we're going to take that area of greater distance. We'll probably get a greater volume. Okay? It depends on how accurate my drawing is here, but it looks to me like we should get a greater volume. So we get 2 pi integral 0 to 1 R What's that distance from here to this point, right here? What's that distance from the y-axis? X. H is this height. What's that height equal to? What's this distance equal to? What is it? Well, there's two f of x's. It's x minus x squared. That is correct. It's the top minus the bottom. It's this distance, x, minus this distance, x squared. This height, okay, right here, is x minus x squared. Okay? So we get 2 pi, 0 to 1, x squared, x cubed. We get 2 pi, x cubed over 3, x to the 4th over 4, 0 to 1. We get 2 pi. We get 1/3 minus 1/4. We get 2 pi times 1/12. We get pi over 6. Wow. If this were 30ths, we'd have 4 of them. This would be 5 of them. It's a little tiny bit more. This is what we would think. Carissa.
Can you explain x minus x squared again?
X minus x squared. If you take a look at this rectangle right here, now if you take a look at it, here's y equals x. Here's y equals x squared. What we're looking at is this height right here. This is the height. And what's it equal to? Well, it's equal to this distance, which is x, minus this distance, which is x squared. Okay. Okay. How we doing, okay?
How did you get the 2 pi? Or the
That's part of the formula. The formula is 2 pi r h. Okay? The 2 pi r is that circumference of the circle we use to generate this thing. Okay? Okay, we have one more thing to do with this, and that's this. Let's do another problem here. Let's suppose we have y equals 4 minus x squared. Do I really want to do this? Yeah, I guess. Okay. This area in question. Boy, I don't really want. All right, well, I did it. Okay, I'm going to do it. Okay, so I'm going to do it. So here's what we want to do. We want to take this area about the y-axis. Okay. I've got a choice. I can take my rectangle this way with a delta x and whip it around the y-axis and generate a cylindrical shell and find the volume that way. It's not all that difficult. But there is a choice in that. Okay? I could take a rectangle this way and whip it around the y-axis with a disk. Now, if I take my rectangle this way and get that disk, this is not a delta x, that's a delta y. And everything has to be in terms of y. Theoretically, what you could do is do every one of these problems 2 different ways. One way with respect to x, in which case you either get a disk or a washer, and then with respect to y, in which case you get a shell, or the other way around. Okay? All right? They're always going to be just the opposite, just like that. So let's do this 2 different ways. Okay? Sometimes it's advantageous to do it one way over the other. Okay? Let's do it 2 different ways. First of all, let's take the rectangle this way. Okay. If I take my rectangle this way, what am I going to generate? What this rectangle will generate? What of the 3 that we have? Thank you. Okay. So let's set it up. Let's do the volume is equal to 2 pi integral 0 to 2. Okay. R. This distance is r. What's that distance from the y-axis equal to? X. H is this height. What's that height equal to? Thank you very much. And that integral will give me the exact volume of that solid of revolution. It'll be 2 pi, 0 to 2, 4x minus x cubed. That'll be equal to 2 pi, 4x squared over 2, minus x to the 4th over 4, 0 to 2. That'll be 2 pi, 8 minus 16 over 4 is 4. I'll get 4 to 8 pi. 8 pi cubic units will be the volume of that solid of revolution. I got to tell you, there's a real life application of this. My son, one of my sons, his first job, he was a civil engineer major from Villanova, and his first job was at a construction company out of Boston. And what they had to do is construct this shell, this entertainment shell for the 4th of July. Some singer was going to sing at a certain spot in Boston Harbor or something or other. And they had to erect this tent thing. And this tent was in the form of a parabola, something like this. If you take this around the y-axis, you get a parabola. And part of his job was to find out how much air conditioning he needed. It was going to be the 4th of July, so they needed air conditioning. So they needed the volume underneath this shell. Well, he had some kind of book that gave him these things. But I went to visit him, and he was showing me this thing, which was really cool. And I said, you could do that with calculus. That's an integral. And we did it with calculus. Of course, he had taken Calc 3, but Calc 2, and forgot all. I never
left this in the dust.
Yeah. Well, anyhow, so I did it out for him, and it came out almost to the exact area, the volume that they were given in that book of BTUs that was necessary to construct that certain thing. It was pretty cool. All right, it was pretty interesting. It was good. Good stuff. All right. Anyhow, that's the son that's now working for G. O'Connell and Sons, the construction company. He started working in Boston, and that was like his first job he had to do, first task. Okay, 8 pi. Now, we could do this a totally different way. We could take a rectangle this way with a delta y and whip that thing around the y-axis. That rectangle is going to generate what?
X equals the square root of 4 minus 1.
What? Huh?
If you rejumble the equation, you should get x equals square root.
Oh yeah, I'm going to have to solve for x. You're absolutely right. But my first question is, what method are we going to have to use? What will that generate, that rectangle? A what? A disk. Okay, that's a disk. It's perpendicular with no distance between them, no space. So it's a disk. Okay? But you're right, we're going to have to do that. Okay. So here we go. This is with disk now. That volume is pi, the integral. Now, everything is in terms of y. What are my limits on y? Where's y going? The x was going from 0 to 2. Where are my y's going? 0 to 4. And it's r squared. That's this right here squared. What is the distance from the y-axis? What is the distance from here to here? Yes, Karen?
The square root of 4 minus 1.
Yes, it's what delta. It's x, which is what your answer has been all along. But we're in terms of y. So what we have to do is this. This distance is x. The distance from the y-axis is x. Okay? And we're going to square it. But since we're in terms of y, this has to be converted to a y. So what is x squared in terms of y? To solve for x squared in terms of y. X squared is equal to 4 minus y. Now what you guys did, which is not wrong, you solve for x and get the square root, but we're going to have to square it, so I don't need the square root, is what I'm saying. Okay? dy. Please note that this integral is a lot easier than the other integral. This is a really simple integral. Okay? It looks totally different from the integral we had here. Matter of fact, it looks so different that it's going to be impossible to give us the same answer, right? Something must be wrong, because the integrals are totally different. So let's check it out. Pi, integrate it, we get 4y minus y squared over 2. Wow, there's no way this can come out, right? Because look at it, it's totally different. This is cubic, and this is going to 4, and that going to 2. It's 2 pi, this is only pi. Let's check it out, let's do it. 4, 16 minus 16 over 2, 8. What do we get? 8 pi. It had to be the same for Pete's sake, okay?
Is that because it's a,
What's that?
is that because it's a curve?
No, it's because we did the same problem 2 different ways. We found the same volume 2 different ways. One way with respect to x, one way with respect to y. Of course, we're going to get the same answer. One method was shells with x's, and we did discs with y's. Yes?
Which one of both is the easiest method?
Depends on you. Depends on you. In this problem, it doesn't really make a difference which one you do. The only time this makes a difference, which method you, wait, we had another question. Hey, you had a question? No, Brendan had a question.
Why did you change the interval from 0 to 4?
Because now we're in terms of y. And y is going from 0 to 4. These rectangles start at 0, and they're going up to 4.
Oh, okay.
Where on x, the rectangles will go from 0 to 2. There's one case, the case where you don't want to use one thing over the other here, is if you had something like this. We don't do much with this. This is not a function with respect to x. This thing here, okay? It's a parabola heading out to the left. Its formula would be x in terms of y squared. It's not a function with respect to x. You don't want to use the x's here because it's a little bit crazy to get this distance here because you have 2 different x's. But that's the only time. Since it's not a function with respect to x, you want to use y's, okay? You want to use y's in this case. I don't know if you're going to run across that at all. You may not, okay? All right, so here's the deal. Theoretically, you can do every one of these problems 2 ways. One with respect to x, with discs or washers, and one with respect to y, with shells, or vice versa, okay? I'm going to give you a problem to do. We'll see how it goes, okay? Then I'm going to pick one student to give me the answer. If that one student has the right answer, we go home. And if that one student does not, we have to do another problem.
Decision who the one that choose B, or
What's that?
do we get to choose the student that you're picking?
Oh, you want to choose? Why, you have somebody in mind you would choose? Besides yourself?
No.
You don't have anybody in mind?
Well, I think we should see who's the most confident, and then
All right, here we go. Okay, let me give you a problem. And I want you to do it 2 ways, is what I really want. Then you can confirm, and once you get the 2 ways to agree, then you know that's the right answer. So, and I don't want to make it complicated. So let's see if we can keep it a little bit simple. Let's take y equals x squared. Okay, here's y equals x squared. And let's take y equals 4. Okay. Here's the area in question. Okay. And here's what I want you to do. I want you to find the volume of the solid generated by revolving this area about the y-axis. Okay? You're going to find the area generated, take this area, revolve it around the y-axis, find the volume of the solid of revolution. And I'd like to have you do it 2 different ways. One with x's, and one with y's. And actually what will happen is if I have one student that's super confident because the 2 answers he or she got are the same, I'll take the answer from one student, okay? And if that answer is correct, we're going to be done, okay? That means I have to do it myself. Okay, so go ahead. And I will do it myself. Wait. Okay. Wow, that is cool.
Would you need another point if you're going to do it around the other axis?
Say that again,
Would you need another point if you're going to do it around the another axis on the second problem, second method? Would you need another point other than?
No, you've got all the points you need. It's going to go from 0, 0 up here to 2, 4.
If you, couldn't you,
Go ahead.
if you take the same function that you use and do it both ways?
That's what I want you to do. Do it both
No.
ways.
If you use the same style, if you do shelf, the shelf for both directions.
That's going to be incorrect.
Stay with me for a second.
Oh, okay.
If you take those and you add them together, you should get a rectangular solid.
I don't know. That doesn't sound good to me. You could try it, but I don't think so. I don't see why you would. You may have something there, but I don't see it. Well, he's laughing. He's confident. What? You've been on tonight, though. You did it 2 ways? Okay, well, let's give some more people a chance.
Same thing.
Tell you what, I'm going to do. I'm going to let you guys decide who the student is. So if there's one student super confident and can convince the others that he or she should be the one, will it be you? What? No. No. Mr. Rivers has it? No. Karen's shaking her head. Usually she's pretty confident. You're not confident? You're not confident? No, you're not? You don't want the whole class to be resting on your shoulders? You don't want to be an Atlas shrugged and lift the whole class up? Yeah, like that. That's it. Tell you what, in 5 minutes, we'll have a student give the answer. Okay? And you guys decide who the student is. And like I said, if one student can convince the others, why? If that answer is wrong, we'll do another. So, Dylan, have you heard of sweatshirts and hoodies and things of the label Supreme? No, huh? Okay. Has anybody? Supreme? sweatshirt that has Supreme as the label, or a hoodie or something like that,
Why are
Supreme?
you thinking of investing?
No, I definitely wouldn't, but in my Calc 3 class, they were talking about today, this company, Supreme, manufactures these things, and they go for like $300 because they have the word Supreme on them.
I'd be happy to sell those.
Yeah, yeah. And the company is a small company, they can't make enough of them. For some reason, they're in huge demand and getting big
Have
dollars.
you ever heard of Johnny Cupcakes?
No.
Wait, is that
I-
the place in DC?
Well, I didn't know about it until they had the guy speak at Stick. It's a T-shirt company, but it's this weird thing where like the store itself looks like a bakery, but they sell T-shirts. But the ridiculous thing is the T-shirts retail for an average of $50 and almost always sell out on a new release.
See, it's the same thing. It's the same thing as this Supreme
It's just
thing.
some like hipster kid that makes weird shirts with like smiling bacon and eggs on it. People freak out.
I know. I don't get it, but yeah, that's the same thing. It's the same thing.
You did?
Have you seen the waterproofing?
Waterproofing.
There's a company that's been working on waterproofing clothing.
Oh,
So you wear it, and let's say you get a drop of water, just slide right off.
oh, cool. All right, that'd be kind of cool. That's kind of practical. That's kind of good, especially with me because I.
That'd be something I'd be willing to pay $300.
Oh, that's not me then. Some of all my clothes is not worth $300. I know it's hard to believe just looking at the cool way I dress. It wasn't that funny, Louis, all right?
You can never go wrong with pastels.
Louis. Oh, man. Oh, gosh. Oh, jeez. Oh, all right. Somebody's making a case for himself or herself here. Somebody gonna grab the mantle, just carpet diem, right? Seize the day. What's that? All right. Well, you guys decide.
Why don't we all say it all at once? And see what everybody says the most.
Yeah, but then, well, if you're all saying the same thing, I'd accept it. As soon as we,
Same answer for both, so I'm going to trust them.
Yeah.
maybe you guys want to converse and compare answers.
I couldn't get it. I lost it.
Wait, if we say an answer out loud, even though it's not directed towards you, does that still count as answering it?
No, because in 1 minute I'm going to ask one student
Yeah, anyone else?
to give me the answer.
Yeah, I got
A pie.
A pie on both of them.
I got a pie.
There we
I
go.
got A pie.
So the one, forget the 1 minute. Who's the one student? Sam?
Yeah,
What do you say?
A pie.
A pie? Yes, that's it. We're done.
You had to fool me for a second, bro.
Here's the deal. You know what I realized after I started doing it? It's the same thing as the last problem. Because the last
Same
problem
thing.
went from here down to here, and it's the same volume.
I
So
realized
it's
that, right? So I got the right answer, so I knew I had the right answer.
That's what it does. It's the same thing.
Like a minute after you asked.
Oh, yeah. All right. Okay, so your homework is 7-2, 7-3. 7-2, 7-3.
Yeah, trust me, the Adderall stopped working. The Almighty was just digging at me.